Welcome back to the deep dive. Today, we are getting really surgical with financial stats.
We are. We're talking asset returns, volatility.
And really, why that single number you always hear, the average, is, well, probably not giving you the full story.
Not even close.
So our mission today is to figure out how analysts find the center of market data, how they measure its spread, and why they get so obsessed with the specific ways they summarize it.
It's the absolute foundation of investment analysis. I mean, every single decision from setting risk budgets to defining what you think an expected return is, it all starts right here.
With trying to figure out what the data is actually telling you.
Exactly.
Yeah.
And sure, you can look at a histogram or a frequency distribution, see the whole shape of the returns for something like the EAA equity index we'll be using.
But you can't just hand someone a chart. You need a single number.
You need that one number to represent the typical outcome. And that's where the journey begins.
Okay, so let's start this journey with the absolute classic, the arithmetic mean.
Right. The workhorse. It's the default, the number everyone just reaches for.
The one we all learned in school. Add everything up.
And divide by how many things you added. We call it the sample mean, or dollar. It's simple, it's clean, and it uses every single piece of data you have.
But that's the thing, isn't it? The fact that it uses every data point, that's also the risk.
That's the entire problem in a nutshell.
Yeah.
Especially in finance.
Because market returns are not neat and tidy. You get these wild spikes, these massive plunges, the outliers.
And the mean is incredibly sensitive to them. One really bad day or one, unbelievably good day can just drag that average completely away from where most of the data is actually clustered.
So if the whole point of the mean is to find the typical result,
An outlier skewed mean just fails that test completely.
which is why we need alternatives, and the most common defense against this whole outlier problem is the median, the middle ground.
Yes, the median. It's so simple in concept, you just sort all your data points from lowest to highest.
And you pick the one in the dead center.
That's it. It doesn't care if the highest value is up 10% or 10,000%. The median doesn't move. It's all about position.
So its big advantage is that it's robust. It's basically immune to those crazy extremes that mess up the mean.
Exactly. If you're looking at things like housing prices or income, data that's famously skewed by a few mega mansions or billionaires,
The median gives you a much better picture of reality for the average person.
it's absolutely the superior measure for that kind of skewed data. But, and there's a but for analysts,
Yeah.
the drawback is that it only cares about that one middle position. It ignores the actual values of all the other data points, and that makes it what the sources call less mathematically tractable.
Meaning it's just harder to use in more complex statistical formulas down the road.
You got it. Which brings us to the third one, the mode.
The most frequently occurring value.
Right. And the mode is great for some things, like, finding out the most popular car color sold last year.
But for financial returns, not so much.
Almost useless. I mean, when you're dealing with continuous data, like a stock index's daily percentage change, it's just so rare to get the exact same number twice. You might get 0.51% one day and 0.52 the next.
They're all unique values, so what do analysts do instead?
They shift their thinking. They look for the modal interval.
Okay, so not a single number, but a range.
Right. You group the data into bins, like on a histogram. For that EAA equity index we mentioned, the tallest bar on the chart, the modal interval, was the range from 0.0% to 1.0%.
Ah, so that specific range had more daily returns fall into it than any other range.
Exactly. 555 observations, in fact. So that tells you the most likely range of returns, even if no single number repeated.
That's a really key distinction. Okay, let's circle back to the big headache here, the outlier. So an analyst sees some extreme value, a 10 standard deviation move or something.
Right. And they're at a crossroads.
Is this a genuine, rare market event that actually happened and has to be included?
Or is it just a typo? A data entry error that should just be deleted?
And that judgment call seems like it defines the entire analysis.
It really does. If it's an error, you get rid of it.
Yeah.
Easy. But if it's a legitimate data point, you now have to choose how you want to represent your data. You have basically three options.
Okay, option one, the purist's route.
Do nothing. You just
Okay.
include it, warts and all. It reflects the entire distribution, and it removes any of your own subjective judgment.
And the other two options involve making an adjustment.
Correct. The first is to just delete the extreme values.
Oh,
That gives you what's called the trimmed mean.
and the second.
The second is to replace them with something less extreme. That gives you the Windsorized mean.
I like the trimmed mean. It's just so intuitive. It reminds me of judging in the Olympics or something.
Yes. Gymnastics or diving.
Exactly. They throw out the highest and lowest scores, so one biased judge doesn't skew the whole result.
It works precisely like that. So for a 5% trimmed mean, you sort all the data, you chop off the bottom 2.5% of values, you chop off the top 2.5%.
And then you just calculate the mean of what's left.
Right. You have a smaller sample size, but the average you get is much more representative of that middle chunk of the data.
Okay, but the Windsorized mean is different. It keeps the sample size the same. It's more about substitution than deletion.
Exactly. With a 95% Windsorized mean, you still identify those bottom 2.5% and top 2.5% of values. But instead of deleting them,
You change them.
you change them. You replace all those low values with the value that's right at the 2.5th percentile boundary, and you replace all the high ones with the value at the 97.5th percentile.
So you're basically putting a cap on them. You're saying you can be extreme, but only this extreme.
That's a perfect way to put it. You cap the impact while keeping the total number of observations, which can be really important for some of the more advanced statistical models.
Okay, so trimming shrinks the data. Windsorizing caps it. Let's see what this actually does in the real world with the EAA equity index data. This is where it gets interesting.
It really is. So when we just calculate the simple arithmetic mean, using all 12,258 observations, we get a return of 0.035%.
A tiny positive number. But what happens when we apply these cleaning techniques?
The numbers change. The 5% trimmed mean jumps up pretty significantly to 0.048%.
Wow, okay. And the Windsorized mean?
That also moves higher to 0.038%.
And the fact that both of those adjusted means are higher than the original mean. That's the key insight, right?
That is the whole story. It tells you instantly that the outliers in the original data were big, powerful negative returns.
We're dragging the average down.
Exactly. Those negative outliers were so strong, they pulled the whole average down, even if the bulk of the days were slightly positive or flat.
That's fascinating because if the outliers had been on the positive side, say one day the index jumped 50%.
Then the arithmetic mean would have been much higher than the trimmed mean. But here, we know the risk, the volatility, was mainly coming from those sharp, painful losses.
So knowing why the mean shifted tells you about the shape of the risk, not just the return.
You nailed it. And this leads us to the next logical step. The mean only gives us the center. To really understand risk and distribution, we need to measure the spread.
And that takes us beyond central tendency and into measures of location.
Or, as they're more generally called, quantiles.
Quantiles, the general term for any value that divides the data up into specific, proportions.
Right. And how you divide the data gives them different names. We have percentiles,
Which cut the data into 100 parts.
deciles, which cut it into 10 parts.
Quintiles into 5.
And of course, the most common one for this kind of analysis, quartiles, which divide the data into 4 equal quarters.
And once you start talking about quartiles, you immediately get to the key measure of spread, the interquartile range, or IQR.
The IQR. It sounds technical, but it's just simple subtraction. It's the difference between the third quartile Q3 and the first quartile Q1.
So you're calculating the range that contains the middle 50% of all your data.
And by doing that, you get a really robust measure of volatility that, just like the median, isn't affected by those crazy tail-end extremes.
Okay, let's ground this with the EAA index data again. The median, which is the 50th percentile or Q2, was 0.044%.
Right. So looking at the full list, the first quartile, Q1, or the 25th percentile, was negative 0.293%.
And the third quartile, Q3, the 75th percent.
That came in at positive 0.460%.
So doing the math, Q3 minus Q1, that's 0.460 minus a negative 0.293.
Gives you an IQR of 0.753%.
So that range, just 0.75%, captures the daily return for half of all the observations.
And that number, that 0.753%, is why pictures are so important, because that range forms the central box and probably the most useful visualization tool for this stuff.
The box and whisker plot.
The box and whisker plot.
It's a fantastic tool because it puts everything we've just talked about into one simple image. The box is literally the IQR, stretching from Q1 to Q3.
Yep, and the median is marked clearly with a line inside that box.
And then you have the whiskers extending out from the box.
Right, and this is where it all connects back to the outlier problem. The whiskers aren't just the highest and lowest values. They're often bounded by what we call statistical fences.
And these fences are what analysts use for automatically flagging outliers.
Precisely. It's not just the gut feeling anymore. The fences are calculated. You take the IQR, multiply it by a factor, usually 1.5.
Okay.
You add that to Q3 to get your upper fence, and you subtract it from Q1 to get your lower fence.
So any data point that falls outside those mathematically defined fences is flagged.
It's flagged as a potential outlier. For the EAA index data, using that IQR of 0.753%, the upper fence is calculated to be 1.589%. The lower fence is negative 1.422%.
So those numbers become the statistically defined boundaries of a normal day for that index.
Exactly. And if a return falls outside that, an analyst has to make that conscious choice we talked about before, investigate it, and maybe trim or Winsorize it. The box plot shows you the center, the spread, and the severity of the tails all in one go.
So let's bring this all home. We've gone through the math, the visualization. Why is all this layering going beyond the simple average so essential for you, the investor?
Well, because at the end of the day, quantiles are the bedrock of professional benchmarking.
How so?
Investment managers, their performance isn't just judged on their average return. It's ranked by percentile against all their peers.
Right? You see this with things like Morningstar's star ratings. A five-star fund isn't just good.
It's statistically in the top percentile of his category on risk-adjusted metrics. It gives you immediate objective context. If your fund is in the 40th percentile, you know for a fact that 60% of its peers did better.
And this goes beyond just evaluating managers, right? It's used in building strategies, too.
Oh, absolutely.
Uh,
Especially in quantitative research. A common technique is to sort the entire market into deciles based on some characteristic.
like market capitalization, for instance.
Market cap is the classic example. You sort all companies and put them into 10 equal buckets. The first decile is the smallest 10% of companies, your small caps.
And the 10th decile would be the mega cap giants.
Right. And doing this lets researchers isolate factors. They can track the performance of small caps versus large caps. If you have a strategy that's supposed to capture a small cap premium, ranking by decile is the only way you can actually prove it works. A simple average across the whole market would just wash that effect out entirely.
It really shows the power of going from one number to a full map of the distribution. We started looking for one number for expected return.
And we found out that number is extremely sensitive.
So we found ways to adjust it with trimming and winsorizing, and then use quartiles in the IQR to define the spread and see the whole risk profile.
And the real analytical leap is being able to compare these measures. That moment when we saw the trimmed mean for the EAA index was higher than the arithmetic mean.
We instantly got an insight.
A huge one.
Yeah.
The data was being defined by its big negative tail events.
So this brings up a big question. When an analyst sees a legitimate, massive outlier, something beyond that upper fence of 1.589% or below that lower fence of negative 1.422,
They have to make a call.
do they let that one rare event define the average, or do they adjust it to reflect a more typical environment?
And that's where statistics meets investment philosophy. Are you evaluating a manager on their performance during normal times, or on their ability to navigate those once-in-a-decade meltdowns? The method you choose, mean, trimmed mean, or median, is the answer to that philosophical question.
So what does this all mean for you? If just tweaking how you calculate the average, excluding a few extreme days, can raise a fund's return from 0.035% to 0.048%, how much faith can you put in any single average a manager reports?
You have to demand context.
The median is clearly more robust when things are volatile, but if you don't see the full box and whisker plot, if you can't see Q1, Q3, and where those extremes really are, you're not seeing the manager's full risk profile. The mean might be higher, sure, but the length of those whiskers might be the thing that truly defines